All right, so the last talk of this session is autonomous navigation, mapping, and exploration with Gaussian processes.
Hello, everyone. My name is Mahmoud Ali, a PhD student at Indiana University. So navigation, mapping, and exploration are interconnected tasks. However, most of the existing approaches, such as the SARA project from the Army Research Lab and other designs, implement them as a separate modules, which results in efficient and sometimes brittle behaviors. So we propose a framework to unify the formulation of navigation, mapping, and exploration using Gaussian processes. And our main contributions are, first, a local GB perception model, which detects the free spaces around the robot. Second, a global GB exploration map, which includes the exploration status of the environment. And third, a novel approach to construct the methodological map of the environment. And our system pipeline is explained as follows. We receive the raw point cloud from LiDAR, and then we transform it into spherical coordinate and project it into a circular surface around the robot known as the occupancy surface. Each point on the surface is defined by its azimuth and elevation angles and assigned an occupancy value based on its return distance. Then we use a sparse Gaussian process to model the probability of occupancy over the surface, where like one main advantage of the sparse Gaussian process that it reduces the n training data for the full GB with an m inducing point. And this reduces the time complexity of the full GB from n cubic to nm squared, where m is much less than n. And this allows us to run our model in real time. Then we leverage the uncertainty associated with the predicted SGB occupancy to construct another surface called the variance surface, where the uncertain area on the variance surface corresponds to the free spaces around the robot. And we define the centroids of the uncertain area as GB frontiers. GB frontiers are used as local navigation points. And since they are located at the center of the free spaces, then the robot motion is aligned with the Voronoi diagram of the environment. And this behavior maximizes the clearance from obstacles and reduces the risk of collision. We leverage the uncertainty of another global sparse Gaussian process model to model the exploration status of the environment, where certain area means explode and uncertain means unexplored. Here, our exploration map represents a full scan of LiDAR using only a single point. So, compared to other occupancy mapping techniques, our approach saves a lot of computation and requires less time to update the map at each observation. Finally, since GB frontiers are abstract the local navigable spaces, we use them as the main building block to build the methodological map of the environment. So when the robot enters a new unexplored area, the robot location is added as explored node. One of the GB frontiers is selected as the next navigation subgoal, and other unselected unexplored GB frontiers are added as a frontier node in the methodological map. The results from the simulated indoor environment show that our approach explores the environment faster and with less travel distance than the state-of-art frontier exploration and the graph-based exploration. Then we changed our approach in a simulated unstructured forest, where the smoothness property of the GB was able to handle the noisy point cloud and detect corrective frontiers at a trail intersection, where baseline failed to complete the exploration. Then we tested our approach in a real robot in an indoor corridor to test its ability to detect frontiers at intersection, to connect loops inside the map, and to navigate to the nearest frontier when the robot in the unexplored area. And finally, we validated our approach in a real unstructured forest, where the robot was able to navigate using only local perception and detect corrective frontiers at a trail intersection from the noisy point cloud, and to construct the methodological map in real time. In conclusion, our approach requires less time to update the global exploration map and explore the environment faster than the baselines, and has running time which doesn't explode this time. Thank you, and I'm happy to answer your question.
There's a question over there, please.
Hi, thank you for a great talk. I might miss some part, but I feel like it's kind of 3D version of vector field histogram, like finding frontier from vector field histogram. How do you say it's different from that?
Yeah, actually, like to find gaps or frontiers inside the local perception, there's a lot of geometry method and learn-based method. So instead of having like some geometry equation and math equations, we use GB to learn the navigable spaces around the robot. So I think this is the main difference.
Okay, thank you.
There's a question over here.
Thank you so much. Very interesting work. Can you
you.
provide more? I have the impression that you are defining this GP on a circle, right?
Yeah.
So can you provide more details on how this, like, are you defining like some special kernels for this, and how this information is also exploited at the time of solving the GP and updating information in real time?
Okay, so we convert the point cloud from Cartesian to spherical. So each point on the surface has the azimuth elevation angle as input and the occupancy as output. And like we have the okay, so the uncertainty, like we use the rational quadratic kernel. We tried the squared exponential, but it didn't work. So we tried the rational quadratic kernel. Could you repeat the second part of the question?
If you were exploiting this periodicity somehow when you're solving the GP.
Oh, okay. One advantage here that our domain for the GB is limited. So we have the azimuth axis limited from minus pi to pi, and the elevation limited by the resolution of the LiDAR. So it's like from minus 30 to 30. So we exploit this, like our knowledge about the LiDAR resolution to initiate like the list scale around the elevation and the azimuth angles.
Okay. Thank you so much.
Thank you.
All right, thank you very much.
Okay.